Hello there and welcome to the third video in a series of videos for the operating system chapter. In this video we're going to look at memory management to start off with, so we're going to jump straight in and get on with that. The key design goals for memory management are to allocate enough memory so that each process can run, split memory up so that it can be allocated to processes in paging and segmentation, we're going to look at that later, and ensure security so that other processes cannot access each other's data and allow efficient sharing of memory. And also extend memory by using virtual memory, but only if it's needed. In order to meet these aims, we use something called the memory manager, and the memory manager splits up RAM into workable chunks of storage and allocate those chunks into processes in a fair manner. We need to remember here that RAM holds a number of different things. It holds the operating system, currently running programs, current files and data that you're working on. It also holds memory addressing for lots of different data. So let's look at an example with memory loaded with 4 programs. A, B, C and D. They are my programs loaded. I have a small free block at the end of my RAM. And then if we process program C, for example, we free up a block. And then E comes along, and E is a slot that is too big. There is enough space in RAM, but E is too large to put it in there. So we use 2 different strategies to solve this problem. We can split RAM up into equal chunks so that E will also be split up, and we can put them in smaller, what we call pages. And this option is called paging. It's where memory is divided up into smaller sections, all of the same size. The only problem is, when paging breaks things down into individual pages, we could potentially destroy any logic that's involved there. We can destroy functions and links to procedures, for example, or potentially loops. So obviously, this isn't an ideal solution. A more economical way of doing this is using something called segmentation, and this keeps together logical divisions of programs rather than having fixed page sizes. So we move things into logical blocks. This means that sizes of segments can vary, but they are split and broken down in logical parts. But what happens if RAM is completely full and we can't get any more blocks in there at all? So if RAM is full, it means we can't bring anything from our secondary storage device. Do we prevent the program from running? Well, no, we don't. What we do is we create something called virtual memory, and that's where space on your secondary storage device is allocated to act like RAM. Now, this is incredibly slow, and it's something that you don't tend to do unless absolutely necessary. And if we spend more time moving programs in and out of RAM, we call this disk thrashing. And it makes the computer very, very slow. And that's why we tend to try and avoid it. So, found this in a mark scheme, which was quite useful, I thought, for students. I'll leave this on the screen for a second. Feel free to pause the video and have a quick look at this. This is comparing paging and segmentation together. And it would be nice to ask approximately 6 marker on this question. So do take a look at it. And now we move on to scheduling. And this is the term the operating system uses to define how and when a process is swapped in and out the CPU, thus enabling our multitasking, which I talked about in video 1. But don't get confused at this point, because scheduling must not be confused with interrupts. Interrupts are hardware signals sent to the CPU to inform it that an event external to the CPU or generated by software has occurred, whereas scheduling makes decisions on which process should be run next or which ones should be interrupted, and this is known as something called preempting. So if we know what a scheduler is, we deal with a couple of different process states. The first one is running. When the process has control of the CPU, that is classed as the running process state. When we are ready to run, that means a process is in a queue and waiting for the CPU so that it can be put on and ran. The block state is when a process is waiting on an input and output operation, such as reading from a hard drive or waiting for data from somewhere. That's called blocked. If you look at this diagram then, the process is loaded in memory and it is ready to run on the processor. If it's selected to run and it gets put on the processor, then it's currently in a running state. While this instruction is running on the processor, if it requests more data from somewhere, then it needs to be put on the blocked queue, because while it's waiting for data to be retrieved, we shouldn't be taking up any time on the processor, so we need to put it on the block state to allow other programs to run. So as more programs come in, we need to put things on a ready to run queue. Once loaded into memory, the processes become live and added to the ready to run queue rather than being placed into the running state straight away. It's the job of the scheduler to decide on which process to run next using a scheduling algorithm, and each operating system has a different algorithm that schedules programs. The scheduler will also decide in what position in the queue the new process should be added, and this is based on priority. As discussed in a previous video, the Queen has a very high priority, so she would go ahead of the queue, next in line to the processor. In the running state, this process will be given a certain amount of time to run, and that's called a time slice. So a running process has a number of operations while it's running. 1, it can complete the task and close. 2, it can be interrupted by the scheduler because of a higher priority. 3, it can wait for an input or output and become blocked. Or number 4, it can give up its own CPU time by its own free will. And the final one, the blocked state. When a process is waiting for a device or an external operation to complete, we say that this process is blocked. A process should never be held in the ready to run queue while waiting for an input or output operation to complete, but should relinquish control to another process by placing itself in the block state and thus freeing up the processor for other processes. The next thing we're going to move on to is time slicing. And time slicing is commonly used in multi-user operating systems and is where each user is given a set amount of time or a time slice for processing. The key here is to be as fair as possible, and the system works in a round-robin-like fashion to service all the customers or users while the system is active. The next thing we need to think about is something called polling. And if you think about polling in a voting sense, it's basically asking a question of which party you would like to vote for. And this takes place during a synchronous activity, and that is a process that will block until an activity is completed. So if a synchronous activity is occurring, then poll the device and ask it for its status. And you're going to loop until the device responds with a ready status. That means it's ready to be ran again. A process or an operating system can do something else while waiting for the poll to return ready. This is called busy wait polling, because while we're busy waiting for a response, we ask questions regarding the status of devices, so that means we can make better use of the processor. Now we move on to something called threading. Threading is where a process splits itself up into mini processes known as threads. Each thread will be managed by the scheduler separately, meaning that they could be run in a different order. Now obviously that will cause a number of different issues. As a thread is under the control of the scheduler, it's the scheduler's job to make sure that everything gets ran in order. But the benefit to doing this means we can take advantage of multiple cores. But there are a number of disadvantages as well. Firstly, synchronization. You have no control over the order that the threads are done, and it could lead to a situation where a thread cannot continue until another thread has completed. So it's important that your scheduler organizes the synchronization. Programming a multi-threaded environment is much more challenging, and there are no guarantees on the sequence. Each thread can access the same data, and therefore there could be a situation where one thread fails due to changes made by another thread. And finally, two threads running on separate cores could access the same data at the same time. When one thread is using the set of data, the other thread must wait. And this is sometimes known as a mutex lock, where one person's locked out while someone else is updating, and then they come out, the lock changes over, someone else uses the data, and so on and so forth. So that's it for our chapter on operating systems. If you've got any questions, please feel free to put them in the comments or send me an email, and I will get back to you as soon as possible. Thanks for watching.